Hello, my name is Alan Cha, and today I'll be presenting a principled approach to GraphQL Query Cost Analysis on behalf of my co-authors Eric Wittern, Guillaume Baudard, James C. Davis, Louis Mandel, and Jim A. Laredo. The landscape of web APIs is constantly evolving. A recent web API model is GraphQL, which is both a query language and a runtime for fulfilling those queries. The advantage of GraphQL is that clients can express the data they want to receive, and servers will respond with exactly the required data. To better illustrate how GraphQL works, let's compare two hypothetical social media APIs, one using REST architecture and one using GraphQL. Given the task of retrieving the names of a user's friends, how would we approach this task in REST? First, we would make a query to the user. Then the API would respond with some user data, including the IDs of the user's friends. And with these IDs, we would make follow-up queries. Lastly, we can parse responses in order to get the names. Alternatively, how would we approach the same task in GraphQL? In GraphQL, we can construct a query to obtain exactly the data that we need. The API should respond with the names and the data structure that reflects the query. As you can see, there are a number of advantages that GraphQL provides, including reducing round trips, limiting overfetching, and minimizing parsing. Because of the benefits, interest in GraphQL has been increasing steadily, and many companies have begun to adopt GraphQL. However, GraphQL is not strictly superior to REST. While GraphQL's flexibility can allow clients to better describe their data requirements, it also makes it difficult to determine the resources that will be consumed by performing a certain query. For example, here we show three queries that differ in length linearly, but the amount of data that these queries will fetch differ exponentially. The reason why these queries can have exponentially large response sizes is list fields, which returns a number of objects. In this case, the friends field returns multiple user objects, which in turn can query for even more user objects. A single GraphQL query can be equivalent to potentially thousands of REST calls. In addition to performance issues, this excessive resource use can make GraphQL service providers vulnerable to a denial of service attack. With the quick growth of GraphQL and the potential attack vector, it is natural to ask, are GraphQL APIs protected? We performed a survey using a list of publicly available GraphQL APIs on apis.guru, and we learned that the vast majority, 83%, do not describe any kind of query analysis. A GraphQL Query Cost Analysis measures the cost of a query. While GraphQL Query Cost Analyses do exist, they do not seem to be widely used. As a result, we set out to understand existing query cost analyses and improve upon them. Query cost analyses fall under two camps, dynamic and static. While dynamic analyses calculate the cost of a query as the query is being executed, static analyses calculate the cost of a query before the query is executed. As a dynamic analysis steps through a query, it will probe the backend for exact list sizes. However, by querying the backend potentially numerous times, the runtime cost will add up. In addition, configuring the analysis to probe the backend will require substantial engineering effort. In some cases, it may even be impossible. On the other hand, a static analysis assumes a pathological data graph. As it steps through a query, it uses an external configuration to obtain upper bound list sizes. Therefore, the analysis doesn't need to be integrated into the backend. To summarize, dynamic cost analyses are accurate. However, we argue that they are too costly in a large-scale production environment. The engineering cost is one thing, but the runtime load may even outweigh the benefits of using a query analysis. On the other hand, static cost analyses are fast and generalizable because they don't need to probe the backend. It simply relies on the configuration. As a result, we believe that a robust static cost analysis is key to helping GraphQL providers protect their APIs. However, existing static analyses cannot handle common GraphQL conventions, have limited configurability, and only work for simple GraphQL interfaces. Our analysis follows the paradigm of static query analysis, but differ from existing analyses in a number of ways. 1. We provide two distinct definitions of query complexity. Whereas existing analyses only provide a single complexity measure, we believe that our two measures of query complexity better reflects how GraphQL queries are executed. 2. Our analysis can handle common schema conventions. It can also take advantage of conventions to simplify configuration. 3. We build our analysis on formal GraphQL semantics. This allows us to prove that our analysis is correct and produces not just an upper bound, but a tight one. And lastly, 4, we performed the first evaluation of such an analysis on real-world APIs. To better illustrate how our analysis works, we need to first take a deep dive into GraphQL. A GraphQL interface is composed of a schema and a set of resolvers. A schema defines the shape of the data graph, whereas the resolvers fetches the data. First, let's take a look at the schema. The type keyword allows you to define object types. Object types have fields. Some fields can also have arguments. And all fields must have a return type. Creating GraphQL queries is just a matter of composing fields. In this case, we are querying for the user with user ID 1 and his name. And here's where resolvers come into play. Each field has its own resolver, and resolvers are small functions that contain arbitrary code that returns data. In this case, the user field has some resolver that will fetch a user object, and the name field has a resolver that will extract the name field from said user object. Because of GraphQL's robust type system, leaf fields, such as the name field, are trivial and can be omitted. Likewise, for the rest of the talk, we will focus on distinct objects and resolvers returning objects. With a list return type, it is possible to query for much more data. For example, I added a friends field on the user type, which can query for a number of users. If list fields are nested within each other, then the size of the response data, as well as the number of resolvers, will grow exponentially. You can begin to see how a static analysis can work. If we know the maximum sizes of list fields from a configuration, it is possible to calculate an upper bound on the size of the response data and the number of resolvers that will be called. Say we want to calculate the maximum response size. Assuming the friends field will return at most 3 users, we can calculate that the query as a whole will return at most 4 users, 1 from the initial user field, and another 3 from the friends field. In our response, we can verify that there are only 3 users, which is below the aforementioned upper bound. Given the same assumption as before, we can also calculate the maximum number of resolvers, which is 1 user field and 1 friends field. In a response, it is the same. In this particular example, the maximum list size did not come into play, but with more nesting than we would see being utilized. In the previous examples, we calculated the response size and the maximum number of resolvers. If we assign a weight to each type and a weight to each resolver, then we can calculate 2 weighted recursive sums that will represent the complexity of the query. We define the former as type complexity and the latter as resolve complexity. Here are the formalizations of the complexities. The type complexity is a product of the maximum list size and the sum of the type weight and the type complexity of the subquery. The resolve complexity is the sum of the resolve weight and the product of the maximum list size and the resolve complexity of the subquery. We believe GraphQL service providers will benefit from either measure, leveraging them to inform load balancing, threat prevention, resolver resource allocation, or request pricing based on the response size or execution cost. We also believe GraphQL clients will benefit from understanding the type complexity of a query, which may affect their contracts with GraphQL services and network providers or their caching policies. So how is the analysis configured? Unless our analysis accounts for common GraphQL design practices, the resulting bound may not be accurate. One particularly important practice is pagination. So how does pagination in GraphQL work, and how does our analysis handle it? GraphQL has 2 pagination conventions, and they are slicing and connection. If no pagination is being used, then a list field can return any number of objects. In this case, you can see that the friends field returns 5 users. The slicing pattern uses what are known as limit arguments to bound the sizes of lists. As you can see here, the limit argument forces the friends field to return at most 3 user objects. To clarify, limit arguments can have names other than limit. Some other common limit arguments are first and last. The connections pattern is similar to the slicing pattern, but can allow for more intricate pagination. It also uses limit arguments, but it also has connection and edge types, which introduces extra levels of indirection. As you can see, the friends field does not return users, but instead a user connection object that contains the users. Here we can see some sample configurations. There is a section for resolver configuration and a section for type configuration. Resolvers and types are identified by their names, but we also allow regular expressions and wildcards. We can assign resolver weights and type weights among other properties. For example, for unpaginated list fields, we can set a default limit which will represent the maximum number of objects that the field will return. For the slicing pattern, we can identify limit arguments. If a limit argument is used in a query, then the analysis will use the argument value as the maximum number of objects that the field will return. Lastly, for the connections pattern, we set not only the limit arguments, but also the limited fields. The limited fields allows analysis to properly handle the indirection in the connections pattern. Now that we have described our analysis and its configuration, it is time to talk about its evaluation. We propose 5 research questions that can be used to understand the effectiveness of our analysis. 1. Can the analysis be applied to real-world GraphQL APIs? 2. Does analysis produce cost upper bounds? 3. Are the bounds useful or close enough to the actual costs? 4. Is our analysis cheap enough for use in API management? And 5. How does our approach compare to other solutions? In order to properly evaluate our analysis, we need to test our analysis on some real-world queries. Unfortunately, we cannot find a publicly available corpus. So we also developed and open source a GraphQL query generator, and we used it to create a corpus containing 10,000 unique and anonymized query response pairs from the GitHub and Yelp APIs. The first research question is, can the analysis be applied to real-world GraphQL APIs? Because our analysis is static, we did not need to integrate it into the GitHub or Yelp backends. We only needed to provide a configuration. We found configuring the limit arguments in the GitHub and Yelp APIs straightforward. Both APIs use consistent names that can be configured using wildcards and regular expressions concisely. In addition, GitHub uses the connections pattern, which we configured using limited fields. We also found configuring default limits to be straightforward. We determined appropriate values from the API documentation and experimental queries. However, for API providers, this process should be even easier as they should have these numbers readily available. Therefore, we conclude that our analysis can indeed be applied to real-world GraphQL APIs. The second research question is, does analysis produce cost upper bounds? We present 4 charts plotting the predicted Yelp and GitHub type and resolve complexities against the actual values. The red line represents when the predicted complexity matches the actual complexity. In other words, a perfect prediction. Points above the red line are overestimations, while points below are underestimations. As you can see, we have no underestimations. Additionally, most points cluster near the red line. Chart A has the most overestimation, but overestimation can be mitigated, which we discussed in the paper. In any case, we can conclude that the analysis does produce upper bounds. Naturally, the next question to ask is, are the bounds useful? In other words, close enough to the actual costs. The chart here shows cumulative levels of overestimation for all queries and typical queries, a category of queries that are similar to size to example queries provided by GitHub and Yelp. We can see that Yelp resolve complexity and GitHub resolve and type complexity perform well. The majority of these complexities overestimate by less than 25%. A large proportion of these Yelp and GitHub resolve complexities are perfect estimates as well. Overestimation is present, but as mentioned before, it can be mitigated. The fourth research question is our analysis cheap enough for use in API management? We want to see if our analysis could be incorporated into existing request response flows, like in a GraphQL client or an API gateway. We measured runtime costs on a standard 2017 MacBook Pro, and we found that a vast majority of queries could be processed in 7 milliseconds and responses in 4 milliseconds. Therefore, we believe that our analysis is cheap enough for API management. The final research question is, how does our approach compare to other solutions? We compared our analysis against the 3 most popular open source GraphQL query analyses on GitHub and the strategies that the GitHub and Yelp APIs employ. We will refer to the open source libraries as libraries A, B, and C. For fair comparisons against the open source libraries, we propose 2 practical bound questions. 1, how large might the response be? And 2, how many resolver functions might be invoked? The first question is of interest to client and service providers, who both pay the cost of handling the response. We measure this in the number of distinct objects in the response. The second question is of interest to service providers, who pay this cost when generating the response. Here we show our analysis and the 3 open source libraries tackling the first bound question. Library A, while it does not have any underestimation, has gross overestimation and striations. This is because it cannot use limit arguments. As a result, it can only be configured using default limits. Therefore, we set the default limits to 100, the maximum number of objects that GitHub will return for any particular field, leading to severe overestimation and striations. Library B and C are related, and hence their charts look the same. Both libraries show gross underestimation, which is problematic for our query cost analysis. This is because they cannot use default limits. As a result, unpaginated lists and paginated lists with default values are not counted properly. Additionally, they cannot handle the connection's pagination pattern, causing overestimation. Regarding the second bound question, how many resolver functions might be invoked, none of the open source libraries can be configured to do this. Because of the limitations of all three libraries, we conclude that our analysis outperforms these open source solutions. Now let's discuss the two closed source solutions. GitHub's GraphQL API relies on two static analyses, which can answer bound question 1 and bound question 2, but with limitations. For example, their node limit analysis disregards types associated with the connection's pattern. Meanwhile, their call score analysis only counts resolvers that return connection types. However, we think there may be a few reasons why our analysis may outperform GitHub's solution. Firstly, GitHub static analyses cannot be weighted. Weighting is important because arbitrary types and resolvers will have different resource footprints. A repository object will likely have a bigger footprint than an issue object. Secondly, GitHub's over-reliance on the connections pattern may be problematic. When our study began, GitHub shared a shortcoming with Library B and Library C. It did not properly handle unpaginated lists. We reported this possible denial of service vector, and GitHub confirmed the issue and have since patched their analysis. Yelp's GraphQL analysis has both static and dynamic components. However, neither one of these measures can effectively answer the bound questions. Statically, Yelp rejects queries with more than 4 levels of nesting. However, it is still possible to craft expensive queries with this limitation, and it reduces the flexibility that clients have to create queries. Dynamically, Yelp applies rate limits by executing queries and retroactively replenishing the client's remaining rate limits according to the response complexity. It is therefore possible to significantly exceed Yelp's rate limits by submitting a complex query when a client has a small quota remaining. Both of these issues can be resolved by using our analysis. Our analysis can provide more insight into the complexity of queries than levels of nesting alone. In addition, our analysis can prevent users from using more than their allocated quota by determining the complexity of a query before rather than after issuing it. Thus, we conclude that our analysis also outperforms the closed source solutions. So, to summarize our contributions, 1. We provide two distinct definitions of query complexity, type complexity and resolve complexity. They reflect how GraphQL queries are executed and are useful to both service providers and clients in the realm of API management. 2. Unlike existing static analyses, our analysis can handle common schema conventions. We are able to utilize not only pagination conventions, but also naming conventions, which allows our analysis to produce better estimates with less configuration. 3. We build our analysis on formal GraphQL semantics, which allows us to prove that our analysis is correct and produces not just an upper bound, but a tight one. And lastly, 4. We performed the first evaluation of such an analysis on real-world APIs, in addition to open sourcing a GraphQL query generator and releasing a corpus of GraphQL query response pairs for future research efforts. Thank you for listening to our talk.